section, I am going to demonstrate how to solve a given network during transient period by conventional method and Laplace transform method. So we know practical circuits are series and parallel combination of circuit elements like this. Whenever transient become, so we can't write ordinary voltage equations. Instead, we need to write differential equation governing the system. Here we can see a transient happen for an RLC series circuit. Here transient occurs for RL series circuit. In this circuit, we can have different resistors, inductors and capacitors with the series and parallel combination. To study the transient behavior, we need to write the differential equation governing the system. So first step of solving this type of problem is we need to write the differential equation governing the system, and we need to solve the differential equation by means of conventional or Laplace transform method. We need to study an important concept, that is order of the system. So that is very much important in control system. So the order of system determines the order of differential equation. In order to find the order of the system, what we need to do is you just need to count number of energy storage elements. So in this case, number of energy storage elements is 1. So order of the system is 1. That is, the order of differential equation is 1. In this case, the order of differential equations is 2. Why? Because we can have 2 energy storage elements. In this case, 1, 2, 3 energy storage elements are there. Therefore, the order of this network is 3. So while solving a transient behavior of a particular network, we need to write the differential equation governing the system first. So let's consider this circuit for that one. Initially, the circuit is in open condition. So at t is equal to 0 minus, just before switching, inductor current is assumed to be 0. And immediately after switching, that is at t is equal to 0 plus, IL is equal to 0. Now let's apply KVL over here immediately after switch is getting closed. Inductor opposes abrupt change in current through that inductor. So applying KVL at t is equal to 0 plus, we can write this voltage equation. That is, V is equal to R into I plus L into di by dt. In order to solve differential equation, we need to find complementary function and particular integral associated with that equation. In order to solve this differential equation, we need to write in this model. We need to replace d by dt with capital D plus R by L into I, which is equal to V by L into e raised to 0t. Then we need to write auxiliary equation governing the system. So in order to obtain auxiliary equation, we need to replace d with m and equate this part is equal to 0. That is, m plus r by l is equal to 0. While solving, you can obtain m is equal to minus r by l. Here there is only one root. So we can write the complementary function as c1 e raised to minus r by l into t. So complementary function gives transient term, that is decaying term. Let it be equation number 1. So C1 we can obtain from initial condition. The particular integral can be found out in this way: Q divided by FD. Here D need to replace with A. Our Q is V by L e raised to 0t. In general, we can say like this: particular integral is equal to 1 by F of A into Q, that is V by L e raised to at. In our case, A is 0. So this equation become 1 by 0 plus R by L into V by L. Solving, we can obtain particular integral as V by R. Now the response is the sum of CF and particular integral. So CF is obtained as C1 e raised to minus R by LT plus particular integral is obtained as V by R. As we know, at t is equal to 0 plus, The inductor current will retain as previous current. Previous current is 0. So when we are substituting IL as 0 in this case at t is equal to 0, we can obtain C1 as minus V by R. Now substituting IL can be obtained as C1. What is C1 we got? Minus V by R e raised to minus R by L into T plus V by R. So as seen here, complementary function is this part. It is exponential decay components. So this indicate transient response. And V by R, this is a particular integral. So particular integral indicate steady state response. So simplifying, we can obtain V by R into 1 minus e raised to minus T by L by R. In RL circuit, L by R is termed as time constant tau. So when we are considering tau, this equation can further simplified by V by R 1 minus e raised to minus T by tau. So this is the expression for finding out the current through the inductor during transient. So as steady state, this part is not there. So it will retain as V by R. So when we are plotting the characteristics based on time, the current versus time plot is shown here. As t is equal to 0, inductor current is 0 and slowly it starts rising and finally it attains steady state value. So whenever t become tau, this part become e raised to minus 1. Corresponding value of current is 63.21 percentage of this final value. Time required to reach the current to 63.21 percentage of its final value is known as time constant of the system. Now let's see how to solve the above problem by means of Laplace transform approach. As we discussed earlier, the first step in solution of a conventional and Laplace transform approach is obtain differential equation governing the system. We got the differential equation governing the system as V is equal to R into I plus L into di by dt. So in order to convert this differential equation, the basic awareness of some Laplace transform is required. So applying voltage suddenly means it is equivalent to a unit step input having value V, magnitude V. So corresponding to unit step, the Laplace transform is A by S. Here it is V by S, where A is magnitude. So here magnitude of the voltage is V. So V by S is the Laplace transform corresponding to V. Laplace transform of I is represented by capital I of S. And Laplace transform of differential equation is S into capital I of S. So this is the equation in S domain when we are converting this differential equation into S domain. So second step is obtain Laplace transform of this equation. So what is Laplace transform of this equation? S into I of S plus R by L into I of S minus V by S into L is equal to 0. Taking the coefficient of I of S term like this, I of S into S plus R by L is equal to V by Ls. So from this we can find out the expression for Is. Is is equal to V by L all divided by S into S plus R by L. Let it be equation number 2. So next step is to find out inverse Laplace transform of this equation. For that we need to use partial fraction expansion. Here we can have two terms, S and S plus R by L. So I of S is equal to A by S plus B by S plus R by L. In order to find out A, we need to multiply this equation with S and equate S as 0 like this. Here S and S get cancelled. By solving, you can obtain A as V by R. Similarly, in order to find out B, We need to multiply this equation with S plus R by L and equate S is equal to minus R by L in this equation, just like this. After solving, we can obtain B as minus V by R. Now we can write this equation as I of S is equal to V by R by S minus V by R upon S plus R by L. When we are finding out inverse Laplace transform of this equation, we can obtain I of t is equal to V by R minus V by R e raised to minus R by L into t. Further simplifying, the response current is obtained as V by R into 1 minus e raised to minus t by tau. As seen from here, for t tends to infinity, this term won't be there. Under that condition, I of t is obtained as V by R. That response is steady state response. So corresponding to steady state, current is V by R. Corresponding to transient, decaying component will be there. Corresponding to any time for t greater than 0, we can obtain current through this inductor using this expression.